Good morning, TA, CS230 teaching staff. My name is Raul,
I'm
and
Phil.
yeah, he's Phil. And today we're gonna present a quick video about our haptic vest, or the model behind the haptic vest that we designed for this class.
So if you've seen Ready Player One, you might be familiar with the concept of having a garment that reacts to its environment and makes you feel vibrations or movement on your body. The idea is to create a similar vest, but one that actually processes images live from your surroundings instead of taking them from a video game. So what we want to do is create a image model that is able to take images of just your surroundings and predict whether there's a person in it, a car, or neither. And that way we can transduce different vibrations onto your vest. So if you're visually impaired, for example, you'd be able to know what is around you.
Yeah. For the data set in this project, we joined two data sets. We got most of the images at first from the Coco data set, but we were having a lot of trouble classifying cars. So we decided to get images from cars from the Stanford Cars data set, and then we combined both data sets into one. In total, we got over 80,000 images that were distributed as following.
So the idea was on the left is what we started with. The pure Coco data set had lots of pictures of neither thing, lots of pictures of people, but very few pictures of cars. We decided that even looking at the images of cars, they didn't fit the ground truth distribution that we wanted to test, whereas the Stanford Cars dataset did. And so we migrated to a dataset where we had a better balance over the three categories and also a closer to ground truth distribution.
Yeah. Regarding the model of our classifier, we decided to use transfer learning, so to use a pre-trained mobile net, both the V1 and the V2 models, and then add some of our layers, then do some fine-tuning later to adapt to our data set and to our needs. So as you can see in this diagram, for the mobile net V1, we're using a 128 by 128 by 3 image. For the MobileNet V2 is a slightly smaller image. This image is being piped through the MobileNet pre-trained model. Then we have a global average pooling layer, then a dropout layer, a dense layer, and then a softmax function that's going to classify that image into the three classes that we just discussed.
We decided that our project needed three different metrics. So on the one hand, we needed to measure the accuracy of this project. How well was it classifying the three labels? But because we wanted to put this on a haptic garment, we need this to be able to run on small edge devices. For example, the Raspberry Pi 4 or the Arduino Sense BLE. And to do that, we decided that we would introduce two satisficing metrics. One, the model size had to be no bigger than 1 megabyte, the TF-Lite file. And two, the classification time couldn't take longer than a second because you want to be able to react in real time to the things moving around you.
Yeah. So here's a quick chart with the model accuracy. First, as we mentioned, we tried two different approaches, training our own model on top of MobileNet V1 as well as MobileNet V2. And we also tried two different variations, one with data augmentation and one without it. As you can see, the model that performed the best was the one trained on top of MobileNet V2 with no data augmentation. In the next slide, we can check out some data about it.
These are the learning curves for the MobileNet V2 without data augmentation. As you can see, they're quite flat. We think that the reason for this is that we're showing 32 times 2,000 images on each epoch to the model, which means that throughout one epoch, so throughout the first 0th epoch, it's actually getting a good chance to learn the function quite well. And so by the time it's reached the end of that 0th epoch, it's already achieving upwards of 80% accuracy.
Yeah. Here we have a simple confusion matrix that we use to debug the model just to understand how well it was doing with the person images from Coco and the car images from Cars dataset. We can see that it's performing a lot better with the car images that we got from the Stanford dataset. Yeah.
Yeah, and then given that accuracy of 87.9 on the MobileNet V2, we were able to take that model with about 400,000 parameters convert it into a TF Lite file of two different types, one which is unquantized and one which is quantized. And so what that means is the unquantized file has float 32s as the weights and parameters, as the weights and biases, and the quantized file uses int8s, which loses a little bit of precision, but drastically reduces the size of the file, meaning that we could meet for both V1 and V2 the satisficing metric for model size. You might also notice that even though MobileNet version 1 is half the size of MobileNet version 2, it was only 1.3% less accurate. So there's, even though these are both satisfied, the trade-off is still there in terms of size and accuracy.
Regarding timing, which was our second satisficing metric, we got all the models, both the quantized and the non-quantized ones, to run in less than 0.015 seconds on the Raspberry Pi Model 4B that we have. So yeah, we managed to achieve all the metrics that we defined for this project. So we'd like to thank you for an amazing quarter. Thank Joe Chang for all the help as this project mentor, and thank Phil for also being a great partner.
Thank you, Raul. Thank you, guys.